Değerli katılımcılar, değerli dostlar, sosyal medya platformları üzerinden bizi izleyen bilim dostu, bilgisever, güzel insanlar. Hepinizi saygı ve sevgiyle selamlıyorum. TÜBİTAK Temel Bilimler Araştırma Enstitüsü, heyecan verici bilimsel eylemleriyle üst düzey ve yenilikçi bilgileri ülkemizin bilim ve eğitim camiasına aktarmaya devam etmektedir. Bugün yine bu vesileyle ve kuantum bilimi ve teknoloji seminer serimiz kapsamında harika bir bölüm gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Bu sefer de çok heyecan verici bir konuyu, maddenin türlü hallarını, bilimsel ve matematik deyimle simetri, topoloji ve maddenin elektronik fazlarını konuşacağız. Konunun dünyaca ünlü isimlerinden son derece değerli bir bilim insanı, ABD Milli Bilimler Akademisi üyesi, Penn State'ten Profesör Doktor Charles Kane bugün bizim konuşmacımızdır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Professor Charles Kane, dear participants, dear colleagues and friends, a very warm hello everyone. It is my pleasure to welcome all of you for this occasion of our Quantum Science and Technology Seminar Series. TÜBİTAK Research Institute for Fundamental Sciences organizes these seminars for national and international audiences, relying on the unifying feature of science for humanity and with the participation of distinguished scientists and great speakers of the world. It is also my distinct pleasure and honor to emphasize that we are absolutely thrilled to have with us Professor Charles Kane, a great scientist and wonderful person from US Penn State. He's going to give a great talk under the title, Symmetry, Topology, and Electronic Phases of Matter. At the end of the talk, we will have a Q&A session where questions can be asked by sending a message through chat button of the Zoom platform. Charles Kane is a Christopher Brown Distinguished Professor of Physics at the University of Pennsylvania. He was born in Urbana, Illinois in 1963 and grew up in Iowa City, Iowa. He graduated from University of Chicago in 1985 with bachelor's degree in physics and received a PhD in physics from MIT in 1989. The following 2 years he spent as a postdoctoral research associate at the IBM Watson Research Center. He has been on the faculty of the University of Pennsylvania since 1991. Charles Kane is a theoretical condensed matter physicist who is known for his theoretical work characterizing Lagrange liquids, the quantum Hall effect, and carbon nanotubes. He predicted the existence of a new class of materials known as topological insulators, which are electrical insulators on the interior, but conduct electricity in a very special way on their surface. Professor Charles Kane has received many awards, including the Oliver Buckley Prize, the Dirac Medal, the Physics Frontiers Prize, and the Benjamin Franklin Medal. He is a fellow of the American Physical Society, and he is a member of US National Academy of Sciences. With this, I want to thank once again Professor Charles Kane for joining us this evening and invite him to stage to begin his talk. Charles?
Okay, well, thank you. Thank you very much. I'm really honored to be able to visit with you this evening. So let me just do my screen share here. Am I, let me just make sure I get this right here. Okay, good. So so you can see my screen correctly?
Yes, it's
okay.
Perfect.
Perfect. Okay, well, wonderful. So and again, so thank you so much for the invitation to speak to you. And you know, I think doing things like this where we have communication across the world is a wonderful thing that we can do, which maybe is you know, taking a little bit of advantage of the trouble that we've all endured over the last 2 years. So again, thank you so much for the invitation. So I want to tell you a story today about symmetry and topology. And so these are two of the big ideas that underlie our understanding of physics and matter. And you know, so symmetry is a familiar idea, especially you know in the beginning stages of physics. You know, I teach beginning physics sometimes for freshmen, undergraduates, and you know, one of the things we tell them is that you know the first thing you think about when you're confronted with a physics problem is you think about symmetry. Okay, because if you can understand the symmetries, it provides a powerful tool for simplifying things and gives you an organizing principle for how to think about them. And, you know, you know, of course, what symmetry is about is it's about what operations leave a system invariant. Okay. And you know, there's a deep idea which goes back to Landau, which is that if you can understand the symmetries of a system, that gives you a tool for classifying and distinguishing distinct phases of matter. Okay, and as you know, a simple example of that is understanding how to classify crystalline matter. And if you look at these pictures, these are some of my favorite pictures. You can sort of see that these pictures sort of behave the way crystals behave. They have symmetries where you can translate, or you can rotate, or you can reflect. And by understanding those symmetries, you can distinguish different kinds of patterns. Okay, and so Landau's idea was that this is a big principle. Classifying the symmetries is how one can distinguish distinct phases of matter. Now, another tool that one has, which is equally deep and fundamental, but maybe a little bit less fundamental, or a little bit less familiar at the beginning stages of physics, is the idea of topology. And what topology is about is it's about what is it that stays the same when something is continuously deformed. Okay, and the classic example for thinking about topology is to think about the sense in which a donut is the same as a coffee cup. Okay, and if you imagine the donut is made out of clay, you can imagine smoothly deforming it, just a little, you know, changing it a little bit each time, and smoothly deforming it in such a way that it starts off as a donut and ends up as a coffee cup. And of course, the hole in the donut has turned into the handle of the coffee cup. Okay, and so there's a sense in which the donut and the coffee cup are the same. And so what mathematicians like to do, of course, topology is a deep and beautiful branch of mathematicians and of mathematics. And what mathematicians like to do is to find out ways of characterizing the sense in which they're the same. Okay, and so so mathematicians introduce what's called a topological invariant, which in this case is called the genus, which just counts the number of holes. Okay, and so that's the sense in which they're the same. Now, you know, the application of topology to physics goes back many decades. Okay, and so this is an old subject which is not so much so new, but what's relatively new, at least you know, which is the physics of the 21st century, is has been a deepening of our understanding of the interplay between symmetry and topology. Okay, and so that's really what I want to tell you about today, and in particular, the interplay of symmetry and topology in regards to our understanding of electronic materials. And so, so what I'm going to start off with is sort of an introduction to explain to you how it is that topology shows up in the band theory of solids, which is the theory that underlies sort of our understanding of many electronic materials. And I will introduce you to the idea of topological insulators in 2 and 3 dimensions, and related ideas can be used to understand topological superconductivity. And so I'll try to explain these to you, and then at the end, I'll try to give you a little bit of a flavor for where we are at the present time and where the field is headed in the future. Okay, and so I want to tell you about electronic phases of matter. And so what I will start with is the simplest and most basic electronic phase of matter, which is the electrical insulator. Okay, and yeah, the insulator. This is again something that that I teach my freshman beginning physics students about. And what I tell them is that in an electrical insulator, the electrons are stuck in place. They're sort of stuck on their home atom, and they can't do anything. Okay, so there's a sense in which the insulating state is the most boring state of matter, because the electrons are just stuck and they don't go anywhere. Nothing happens. And, you know, it's just, you know, you could say that's boring, but there's something actually very interesting about this, which is the fact that an insulator can insulate is in order to really understand that, it is a consequence of quantum mechanics. Okay, because, you know, in quantum mechanics, what quantum mechanics tells you is that in an atom, the energy levels of that electrons can obey are quantized. So the electrons sort of snap into quantized orbitals, and in an inert atom, you know, it costs a finite amount of energy in order to excite the electron to do anything. Okay, and so that's the reason why insulators insulate. It is because there is an energy gap that an electron must overcome in order to do anything. Okay, now you might say an insulator built out of, you know, sort of independent atoms is that is kind of boring, you know, like solid argon. You know, as an electronic material, that's not so exciting. Things get more interesting if you allow the atoms to become closer together and start interacting with each other and forming covalent bonds. Okay, and so the language that was developed to understand the electronic behavior of such electronic insulators goes under the name of the band theory of solids. And, you know, band theory is probably the most consequential, one of the most consequential theories that we have in physics. It's the theory that underlies our understanding of all kinds of electronic materials, okay? Like silicon, okay? Now, silicon is an electronic material. It's a semiconductor, which is really an insulator. And like any insulator, it has occupied energy levels separated by an energy gap from the empty energy levels. Okay, and you know, our understanding of silicon is a big deal because that underlies all of the electronics technology that we've grown accustomed to in the modern age. It underlies all the technology that allows me to talk to you from across the world. Okay, and you know, and you know, one thing I want to say is that, you know, the band theory of solids gives us very detailed understanding of the electronic structure of materials. Okay, and so this picture here is the band structure of silicon. And I don't want to go into too many details of what all these wiggles, you know, the wiggles on this graph mean. The lesson that I want to get across is that it's complicated. There are many details, okay, and we have mastered those details. But there's another point that I want to make, which is there is a sense in which this complicated electronic structure of silicon is the same as this very simple electronic structure of an atomic insulator. Okay, because you can sort of imagine that, you know, if you start with silicon, you can imagine pulling the atoms apart and getting them, you know, smoothly separating them and having them get further and further apart, and smoothly interpolate between having this, you know, relatively complicated covalent insulator and this much simpler atomic insulator. You can imagine smoothly, you know, connecting the two, and along the way, it stays an insulator the whole time. So there's a sense, which is this sense of topology, that one can smoothly deform in your mind's eye. You can smoothly deform this covalent insulator into an atomic insulator. So there's a sense in which they're the same. Actually, they're kind of the same as the vacuum. The vacuum isn't as empty as you first might have thought. If you think in terms of relativistic quantum mechanics, Dirac's quantum mechanics, then the vacuum has a valence band too. Okay, so the positron is the antiparticle of the electron. Okay, and according to Dirac, a positron is just like a hole in the valence band of a semiconductor. Okay, so it's like removing an electron from the occupied states of a semiconductor. The only difference is that the energy gap is 1,000,000 times bigger. Okay, but the way that we describe mathematically Dirac's vacuum is the same as the way we describe the ground state of a semiconductor. Okay, and so there's a sense in which all of these are the same. Okay, and so I would like to elevate this to a principle, which I'll call the principle of adiabatic continuity, which I'd like to say that insulators are topologically equivalent if they can be continuously deformed into one another while staying an insulator the whole time. Okay, and so this is this notion of topology, and this is a question. The band theory of solids has been around for 90 years. Okay, but this is a question which wasn't really asked until much more recently. Okay, and when you pose it like this, then the question that it poses is whether it's possible. So most insulators you might think are kind of like the trivial atomic insulator. Is it possible that there could be insulators that are different? Okay, and the remarkable answer to this question is yes, that there do exist topological phases that are not adiabatically connected to the trivial insulator, and these are fascinating phases of matter. So in pictures, the trivial insulator is sort of like the sphere, which has no holes in it. It has genus 0, whereas the topological insulators are more like the donut that has a genus of 1. Okay, so in order to introduce you to these topological phases, what I always like to do is to start with the simplest version of a problem, which is simple enough that maybe you can get your head around it. And the simplest version that I can think of a topological insulating state is to think about what happens in one dimension. And in particular, think about a one-dimensional polymer called polyacetylene. Okay, and so polyacetylene is a one-dimensional polymer, which is important in its own right. It's a conducting polymer, but in its simplest form, so it's basically a chain of carbon atoms, okay, and with some hydrogen atoms attached, but it's a one-dimensional chain. And the important thing is that if in its pristine state, if all of the bonds on the chain are the same, then it is a one-dimensional conductor. Okay, because basically there's one mobile electron in every carbon atom, and that one electron forms then a half-filled energy band, which makes it a conductor. But the thing is that this is not what polyacetylene wants to do. What polyacetylene would rather do is it would rather dimerize, by which I mean that it undergoes a distortion where the atoms move in such a way to make it alternate between short and long bonds. Okay, and you see, if it does that, then what it does is it opens up an energy gap. It turns the conductor into an insulator, and it opens up an energy gap so that all of the occupied electronic states sort of go down in energy. So it lowers its energy, okay, and turns it into a electrical insulator. Okay, now the thing that's interesting about this is that there are two ways that you can do it. Okay, so either you can alternate short, long, or you can alternate long, short, short. Okay, and I would like to argue to you that these two different ways of doing it are two topologically distinct insulating phases. Okay, because so if you think about it, this A phase that I'll call that's what happens when you move the green atoms to the left, and the B phase is what you get when you move the green atoms to the right. If U is the distortion, you can't get from U being positive to U being negative without going through U equals 0. And U equals 0 is the undimerized state, which is an electrical conductor. Okay, so you can't get from this insulator to this insulator having it stay an insulator the whole time. And that's what I mean by having the A phase and the B phase being topologically distinct. So these two phases are separated by a topological quantum critical point. Okay, and at the critical point, it's no longer an insulator. Okay, so one thing that what we'd like to be able to do if we declare that these two insulating phases are distinct, we'd like to come up with a way of distinguishing them, sort of the way that we distinguished a sphere from a donut by counting the number of holes in it, by counting the genus. Okay, and so this is actually something that you can do if you write down a simple model for polyacetylene. And the simplest model that you can write down for polyacetylene is to imagine that there's just a single state on each atom. Okay, and so since there are two atoms in each sort of periodic unit cell, then each unit cell has two states, and one can describe this system in terms of a Hamiltonian that's basically a 2x2 matrix. Okay, so one can describe the band structure in terms of a Hamiltonian, which is a function of momentum, which is a 2x2 matrix, which is a function of momentum. Now, in this simple model, and one thing you know about 2x2 matrices is that you can always write them in terms of the Pauli matrices. Okay, sigma x, sigma y, and sigma z, up to just a constant term, which doesn't do anything. And so now the thing about this simple model of polyacetylene, which describes hopping between the A sublattice and the B sublattice, is that this model only involves the X and Y Pauli matrices. So it's like there's a magnetic field that couples to the Pauli matrices, but it's only in the XY plane. And so what this means is that as a function of momentum, and momentum in one dimension is like a circle. Okay, that's what the one-dimensional Brillouin zone is. And so one could distinguish distinct phases by whether, as a function of momentum, this magnetic field wraps around the origin or not. Or one can characterize a winding number that characterizes how many times this magnetic field as a function of momentum wraps around the origin. Okay, and so this is a way of coming up with a topological invariant that distinguishes these two insulating phases. Now, I have to be a little bit honest here. I have made some hidden assumptions. You see there's a little star here. That star means that there are caveats. And the caveats are that I have implicitly assumed that there is some symmetry. Okay, and this actually is an interesting part of the story, because you see the question is, I told you that we can write it in terms of the Pauli matrices. There are three Pauli matrices: sigma x, sigma y, and sigma z. And what is it that prevents me from having a term which is proportional to sigma z? If there was a sigma z term, then I could go from this configuration to this one without cutting through the origin, without having the energy gap be equal to 0. Okay, I just go over the top by turning on a z component of the field. Okay, so something has to prevent that. Okay, and what prevents that is symmetry. Okay, and so there's an interesting interplay here between symmetry and topology. Okay. Now, and it's interesting to think about what the symmetries in this polyacetylene model are. So one symmetry that the simple model of polyacetylene has is a symmetry which we call particle hole symmetry, which is a symmetry that basically says that the conduction band and the valence band are exact mirror images of each other. So it's a symmetry that takes energy to minus energy. Okay, and the simplest model of polyacetylene has this symmetry, and that symmetry guarantees that the z component of this field would be equal to 0. Now, one thing I'll say though is that this particle hole symmetry is not an exact symmetry of real polyacetylene. Okay, so real polyacetylene does not have an exactly symmetric conduction band and valence band. There's no reason for that to be the case. Okay, and if you include more bands or you include further neighbor hopping in this model, then this particle hole symmetry will be violated. But nonetheless, it's a very interesting thing to think about the consequences of this particle hole symmetry. And a little bit later in this talk, I'm going to be talking about a related situation where the particle hole symmetry is a intrinsic exact symmetry. Now, polyacetylene does have other symmetries though. So in particular, it has a rotational symmetry. So if I think about the middle of a bond, then real polyacetylene has a symmetry under 180-degree rotation about the middle of the bond. Okay, so that's a real symmetry, and that symmetry is enough to protect the topological distinction between the A phase and the B phase. Okay, so the A phase and the B phase are still topologically distinct, even in real polyacetylene. Okay, but the point I want to make is that symmetry sort of gives us something which is richer. If we didn't have any symmetry, then the A phase and the B phase would not be topologically distinct. Okay, so symmetry gives us something new. Okay, so the important question though now is, what is the consequence of this topological distinction? Okay, and so here's this, and this consequence is sort of the most important thing, and the most important thing is the existence of topological boundary modes. So the question is, if you have distinct topological phases, then what happens on the boundary that separates them? So you can imagine a domain wall where on one side you're in the A phase and the other side you're in the B phase. Okay, and so just to get our bearings, there's a simple thing that you can think about with this, which is you can imagine the extreme limit in which the bonds on the strong bonds are very strong and the bonds on the weak bonds are equal to 0. So then what you basically have is you just have a bunch of dimers, which are two atoms that are bonded to each other. And you know what's going to happen is that there's going to be sort of a bonding state and an anti-bonding state that are separated by a big energy gap. And that's going to be your, so you have a big, huge energy gap. It's an insulator. Okay. Except, on this domain wall separating the two phases, you can notice that there's an atom that sort of gets left behind. Okay, and so its state is going to still be at 0. And so that's going to be a 0 energy state that is sort of in between these two insulators. Okay, and I'd like to argue to you that this 0 energy state is something that's very special. Okay, now you could say, okay, well, this is in a very extreme limit where I set these bonds, these weak bonds, equal to 0. So you could ask, what happens if I now turn back on these weak bonds? Okay, and so this is a situation where thinking about symmetry is very powerful, because so remember, let's accept that we have this particle hole symmetry, which is a reflection symmetry that takes energy to minus energy, and so that means that for every state at a positive energy, it has to have a partner with equal and opposite negative energy. Okay. And so this 0 mode is special because it is its own partner. So it has the symmetry, but there's just a single state there where 0 and minus 0 are the same. So you can ask then, what happens if I turn these bonds off? Well, nothing can happen to this 0 mode. It has to stay there because it can't move away from zero. Because if it did, then its partner would have to appear out of nowhere, and that can't happen. Okay, so this zero mode is topologically protected. Okay, given this particle hole symmetry. Okay, and so that gives you some idea. There's no way you can get rid of it. Okay, and so this zero mode in fact persists even if you make these weak bonds almost as strong as the strong bonds. Okay, and so now this is a phenomenon that was actually discovered and rediscovered many, many times over the years. And I think it was first discovered by the field theorists, in particular Jakiv and Rebbe, who were interested in studying, the properties of certain field theories, and in particular, the simplest one they could think of was a one-dimensional field theory. And what they what they noticed is that if you have a domain wall, if you have a one-dimensional Dirac fermion, basically mass, and you have a mass for the Dirac fermion that changes sign at a domain wall, then they notice that there is a exact eigenstate at zero energy that's topologically protected. Okay, what I will say, this is actually a very nice calculation to understand. If so, for the students in the audience, if you have not been through the calculation, that it's a fairly simple and straightforward calculation, which is to analyze this one-dimensional Hamiltonian and to show that no matter what, that if as long as the mass changes sign at a domain wall, no matter what the function m of x is, that this is an exact zero energy eigenstate of this Hamiltonian. Okay, and so if you haven't been through this calculation, then I'll assign it as a homework problem for you, and it's a very rewarding calculation to get to the end of. Okay, so the upshot of this is that we have this very special zero mode, and one point that I want to make is that there are two levels that you can think about this on. So one level is to think at the level of single particle quantum mechanics, where, so for instance, I have a Hamiltonian that describes the Hamiltonian for a single particle. And then you can ask, what are the eigenstates and eigenenergies of that Hamiltonian? And there's a particular eigenstate that has zero energy. Okay. And so as a single particle quantum mechanics, one can think of the existence of these zero modes, and that's the consequence. But you see, of course, real polyacetylene has lots of electrons in it. Okay, so it's really a many particle problem. And of course, the way we think about many particle problems when there are no interactions is we solve the single particle problem, and then we populate the single particle states with particles. Okay, with electrons, for example. And so then you fill the states up to the Fermi energy, and then you have a many-body ground state, which is all of the filled single particle states. So thinking about these zero modes in that context is actually quite interesting, because and quite interesting and quite surprising the first time you see this, because if you think about this zero mode, it will either be, so of course, all of the states in the valence band are going to be occupied. And then this zero mode can either be occupied or empty. Those are two different states. Now, since we have this exact mirror, the exact particle hole symmetry, okay, so there's a symmetry taking energy to minus energy, then what that guarantees is that the state in which this state is occupied and the state in which the zero mode is empty, those two states have to have equal and opposite charge. Okay, because exchanging particles and holes is like exchanging it's like exchanging electrons and positrons. It changes the sign of everything, right? And but of course we know that the difference in charge between these two states is E, because they're distinguished by whether this one particular state is occupied or not. And so that means that the charge of these two states is either plus E over 2 or minus E over 2. Okay, so we have half of an electron. Now, we're not actually cutting an electron in half. That's not what we're doing. And it is impossible to cut an electron in half. But somehow we have exactly half an electron here. Okay, so for instance, you can imagine starting off in a system which is everything is in the A phase. Okay, and so you can ask, what are the excitations of that? Well, I can add an electron to that, and the only charged excitations you can have are having charges which are multiples of E. Charge is quantized in units of the electron charge. Okay, so I can add an electron to this insulator, but then if I nucleate a B phase where that electron is, then what I can do is I can split that electron in half into 2 charge E over 2. Okay, so having this topological phase allows us to kind of do the impossible. It allows us to split the indivisible, splitting this electron in half. Okay, you can't have an E over 2 by itself. Okay, but you can have an E over 2 on the boundary between two topological phases. And now, of course, if you have a boundary here, there has to be another boundary. Okay, but that boundary can be far away. Okay, and so so this idea of splitting the indivisible, this is the essence of what topological electronic phases of matter that I'm going to be describing. This is the essence of what they're about. And the remarkable thing is that there are many, many more versions of this type of phenomena. Okay, and so and I want to show you some of these other examples. And so the next example I want to show you is, I want to step it up one dimension to think about a one-dimensional electrical conductor. Okay, so this one-dimensional electrical conductor, it could be the undimerized polyacetylene. Okay, so it's an electrical conductor, so you fill the states up to the Fermi energy. There's states at the Fermi energy, and there are two kinds of states. There's either states which are propagating from right to left, or from left to right, or from right to left. So they're right moving and left moving states with positive or negative group velocities. We give those fancy name. We call them right and left moving chiral fermions. Chiral just means they're moving in one direction. Now, the thing about one-dimensional electrical conductors is that they're very fragile. Okay, because if you put on any potential, then the electrons can scatter from the right to the left. They can scatter back. And if they can scatter back, then they can scatter back and forth. And if they're just scattering back and forth, then they become localized and they never go anywhere. So if you have disorder will localize a one-dimensional conductor and turn it into an insulator. Or if you put on a periodic potential, a weak periodic potential will open up an energy gap, just like what happened in polyacetylene. Okay, and so this one-dimensional electrical conductor is very fragile. Okay, and so wouldn't it be nice if there was some way we could protect this one-dimensional electrical conductor? And what I'd like to do is I'd like to show you a way that we can protect a one-dimensional conductor in a way that's very similar to the example I showed you with polyacetylene. And so what I'm going to do is the following. I'm going to imagine a two-dimensional system which is built out of a whole bunch of one-dimensional conductors. Okay, and if these one-dimensional conductors have a periodic potential on it, that opens up, then the right-left movers, they sort of, they sort of kill each other and open up an energy gap. Okay, so this is a trivial insulator. But when you draw it like this, you realize that there's another option, which is that I can pair up the right and left moving modes in a different way. I can pair them up like this. Okay, so I can imagine that the right moving mode on one wire is paired up with the left moving mode on the next wire. And if I do that, then they will open up an energy gap in the same way. And it'll be inside here, it'll be an insulator. Outside, it's an insulator. Okay, but what you can see is that on the boundary between these two insulators, something very special happens because there is a chiral mode that gets left behind. Okay, just like what happened in the polyacetylene example that I showed you. Okay, so in fact, these two different kinds of insulators are topologically distinct insulators. And on their boundary, there exists a topologically protected chiral fermion boundary mode. Okay, and this it's like there's a one-way a mode for the electrons where the electrons are only propagating from left to right on this mode. Of course, there's a mode that moves from right to left, but it's in a different place. Okay, and again, having this this right moving mode by itself, it's impossible. Okay, in an isolated system, it is impossible to have an unpaired chiral one-way mode. Okay, but it is possible to have it on the boundary between two topological phases. Okay, and so these chiral edge states, if you will, they're really sort of very special and magical things. And again, they're impossible to have in isolation. But if you can separate them using a topological phase, then once you have them, they're impossible to get rid of. Okay, and again, there are two ways two levels that you can think about this on. You can either think about it in the single particle quantum mechanics level, where you're thinking about the eigenstates of a single particle Hamiltonian. So now you can imagine that you have these insulators on either side, and those insulators have single particle states in the valence band and single particle states in the conduction band, and the conduction band and the valence band are separated by an energy gap. Okay, but what happens on the boundary between these two is that there's a single band that connects the conduction band and the valence band, and this band has a positive slope, so it's only moving from it's a one-way conductor. There are only states moving to the right. Okay, and again, you can sort of see from this that there's no way you can get rid of this. Since it connects the valence band to the conduction band, unless you can make the conduction band, the gap, go to zero, there's no way you can get rid of this. So these edge states are topologically protected. Okay, and again, so one level is to think about just the single particle eigenstates. Okay, so then there are going to be states which are inside the single particle energy gap that connect the conduction band to the valence band. The other way you can think about it is you can think about the many-body ground state corresponding to this. Now, of course, in an insulator, you have a many-body ground state that is separated by an energy gap from all of the excited states. The many-body ground state is just the valence band is completely full and the conduction band is completely empty. In order to excite that, you have to cost the finite energy gap. Okay. Now, for these, when you have the edge state, then of course you fill the edge state up to a Fermi energy, and so they're going to be low energy excitations. In this edge state, and one can characterize these low energy excitations in terms of a sort of low energy, in terms of a low energy field theory, basically. Okay, and so one can characterize the many-body edge spectrum as being described by what I'll call a chiral Fermi liquid, which has a simple description in terms of a free fermion, conformal field theory. And this many-body ground state has remarkable quantized properties. Okay, so one thing it has a quantized electrical conductance. So if you imagine, increasing the Fermi energy a little bit, okay, which you can do by applying an electrical voltage to this conductor. Then, if you increase the Fermi energy a little bit, then you're going to have more electrons moving to the right, so you're going to have an extra electrical current flowing. And so that defines an electrical conductance, which is the ratio of the current to the voltage. And that electrical conductance due to this edge state is quantized, is precisely quantized in units of this fundamental constants E squared over H. Okay, and so there's a quantized, so this many particle state has this quantized electrical conductance. It also has a quantized thermal conductance. So if you imagine raising the temperature of the edge a little bit, then there's going to be more heat flowing along the edge because you have, you have excited low energy states on the edge, and that defines a quantized thermal conductance as well. And so these quantized quantities sort of provide a very deep and fundamental characterization of this. I told you that these edge states are impossible by themselves. Okay, and a way that you can say that is that if you tried to write down a theory of this edge state by itself, it's not really well defined. And the sense in which it is not well defined is the sense in which it has what is called an anomaly. Okay, and so there are two kinds of anomalies that this chiral edge state has. It has what's called the chiral anomaly, which is related to the conservation of charge, which characterizes this quantized electrical conductance. And it also has a gravitational anomaly, which is related to this quantized thermal conductance. So these are fundamental characterizations of this, of these edge states. Now, what I'd like to do is now, of course, I'm telling this story a little bit backwards. This phenomena was not discovered by thinking about these kinds of things. It was actually discovered by experiments in the laboratory, studying the properties of electrons in a magnetic field. And so so the best way to actually make this quantized Hall state come to life is by putting electrons in a magnetic field, and you get Landau levels. And one thing I'll say is that this motion where the electrons are sort of going around, backscattering back and forth, it's sort of like cyclotron motion. Okay, so this is just like a Landau level. Okay, so in any case, so of course one has this quantized Hall conductance, which was goes back to the 1980s, and in fact it is measured so accurately, it can be measured experimentally to 1 part in a billion, that this measurement now forms the foundation for the fundamental unit of the kilogram. This actually just happened in the last couple of years. So this measurement is the best measurement you can do of E²/h. And so it means that this is the best measurement you can do to define the kilogram. Okay, so this is this precise quantization of the Hall conductance. Now, just to convince you that this is not a completely closed subject, this quantized thermal Hall conductance was really only measured in the last couple of years. Okay, and so there's a remarkably ingenious experiment by Moti Heiblum, who's at the Weizmann Institute in Israel, and so he developed an ingenious. So it's actually kind of hard to measure heat transport, and so he developed an ingenious technique to do that, and was able to measure this quantized thermal Hall conductance. Now it's not to 1 part in a billion like this, but it's still pretty good. Okay, and so this is a remarkable thing. And so now, what you'd really like to be able to do is you'd like to be able to do this without a magnetic field. Okay, so one thing that's really, in order to get Landau levels, you need a big magnetic field. And so one question you can ask is whether it's in principle possible to do this without a magnetic field. And so the essential thing is you have to be able to tell the edge states which way to go. And what that requires is that you have to find a way of breaking time reversal symmetry. And so what I want to do is I want to introduce the concept of time reversal symmetry, because this is going to figure in to what I have to say. So let me tell you what time reversal symmetry is. So time reversal symmetry is about what happens if you take a motion picture and then you run it backwards and ask, does what you see obey the laws of physics? Now, of course, a magnetic field changes sign under time reversal, because if you run a magnetic field is created by electric currents. And if you run the motion picture, the electric currents go in the opposite direction. So the magnetic field has to go in the opposite direction. Likewise, these one-way edge states, they change direction if you run the motion picture backwards. Another thing which is interesting to think about is, electrons have spin. That's another uniquely quantum mechanical fact about electrons. And, an electron is like a spinning top. So under time reversal, spin up will go to spin down. And it's actually interesting to think about what happens in quantum mechanics with time reversal. And so time reversal actually does two things. It flips the spin. It also introduces a complex conjugation into the wave function. And it does one more thing, which is it gives you this minus sign. And this minus sign is my favorite minus sign. This minus sign is the same minus sign. Perhaps you know that there's a minus sign that if you rotate a electron by 360 degrees, then its wave function picks up a minus sign. Okay, that's the same minus sign. Or there's a minus sign that you get when you interchange two fermions. It's the same minus sign. Okay, and in the context of time reversal symmetry, what this minus sign tells you is if you do time reversal twice, it squares to -1. Okay, and this -1 tells you, it gives you what's called Cramer's theorem, which says that if you have time reversal symmetry, then every state is at least twofold degenerate. Every state has a partner at exactly the same energy. Now, in a sense, this is trivial. This is it's simply the fact that if you have an atom, you can put up spins and down spins in every orbital of an atom, and putting the up spin in and putting the down spin in, if there's no magnetic field, those have the same energy. So that's Cramer's degeneracy. But things are much more interesting and much richer if you're in a situation where you have an interaction between the spin and the orbital degrees of freedom. If you have a spin-orbit interaction, so you can't talk about the spin and the orbital degrees of freedom separately, then Cramer's theorem has a much richer consequence. And so the question I want to ask is, in order to get this integer quantum Hall state, we have to break time reversal. Are there topological phases with unbroken time reversal? And in order to get at this, what I want to do is I want to play the same game that I played before of splitting the indivisible. Okay. And but I want to split the indivisible without violating time reversal symmetry. Okay, so now I have to include spin. So I'm going to start with my one-dimensional electrical conductor. But now I have both up and down spins that can move to the right and both up and down spins that can move to the left. And what I want to do is I want to split this in a way that respects time reversal symmetry. And clearly you can do that because I can split it in such a way that on the top edge, I have up spins going to the right and down spins going to the left. See, because if I run the motion picture backwards, the up spin turns into the down spin, but the right mover turns into the left mover. So it looks the same. Okay. And so, so these edge states have a similar remarkable property to the one-way edge states of the integer quantum Hall state. Okay. In particular, they are protected. So first of all, they're impossible to have just in isolation. You can't just have this completely by itself in a purely one-dimensional system. It's impossible. But once you have them, if they're on the boundary of a topological phase, so you have a pair of them that are spatially separated, then once you have them, it's impossible to get rid of them. They are protected by time reversal symmetry. And they have a kind of anomaly similar to the anomaly of the quantum Hall states, but now it's sort of a Z2 anomaly. And there's a topological invariant that protects that distinguishes this two-dimensional insulator, which is a Z2 topological invariant. Okay, and in order to make this happen, though, it is essential that you have a spin-orbit interaction. And so in order to make this come to life, it's essential that you work with materials that have elements that are very heavy, that are at the bottom of the periodic table, elements that have a strong spin-orbit interaction, like mercury. Okay, and the first idea we had for thinking about this back in the beginning was to think about it in graphene, and graphene actually has a very weak spin-orbit interaction. So the model that we wrote down that did this, we didn't know how to make it come to life in the real world. Okay, but there was an ingenious work by Lawrence Molencap and also Xucheng Zhang that recognized that in mercury cadmium telluride you can precisely make this happen. Okay, and Lawrence Molencap made these quantum well structures out of mercury cadmium telluride and was able to demonstrate the existence of these one-dimensional conducting edge states in this two-dimensional quantum spin Hall insulator. And so this was the beginning of a wonderful chapter in condensed matter physics, where one recognized that these ideas of topological phases of matter have a much wider applicability in many new classes of materials and many new classes of phenomena. And so this was the beginning of a huge thing. And so there are many, many more examples. Let me just tell you. So in 3 dimensions, one can do the same thing. Okay, and again, let me cast this as splitting the indivisible. Let me start with a 2-dimensional electrical conductor, and let me try to split it in half. Okay, and so if I can split a 2-dimensional electrical conductor into 2 impossible 2-dimensional conductors. Now, so this impossible 2-dimensional conducting state is something that has what I would like to call a 2-dimensional surface Dirac cone. So if you've ever learned about graphene has an electronic structure that has a Dirac cone in it. But the thing about graphene is it actually has 4 Dirac cones. Okay, and you can ask yourself the question: is it possible to have just a single one? And the fact is that if you have time reversal symmetry, having a single Dirac cone in a purely 2-dimensional system is impossible. Okay, but it is possible on the boundary of a 3-dimensional topological phase. And that topological phase is called a 3-dimensional topological insulator. Okay, and so an example of a 3-dimensional topological insulator is a material called bismuth selenide. And so bismuth selenide is a 3-dimensional, crystal. It's like a rock. You can hold it in your hand. It's an insulator on the inside, has an energy gap, but on its surface, it has a very special electrical conducting surface that has this single Dirac cone in its electronic structure. And so this this single Dirac cone is something that can be probed experimentally by doing angle resolved photoemission spectroscopy. So Zahid Hassan was the first person to do this on bismuth selenide. So it's basically like taking a snapshot of the taking a picture of the electron of the surface. And let me just say that this picture here shows a sort of textbook perfect single Dirac cone on the surface of the bismuth selenide. Okay, so there are many, many materials that this can do. Now, so let me just see, how am I doing for time? Am I already out of time, or do I have time to tell you a little bit more? So please give me, I don't want to overextend my welcome. Well, if nobody's telling me to shut up, then I think I'll go on for a little bit longer, but I'll try not to go on for too long.
Yeah, sure.
Okay, okay, all right. So, but I won't take too long. So I want to tell you about one other idea, which is another application of this same principle of splitting the indivisible, and this is in the service of trying to do something which would be a sort of grand technological challenge of our day, which is how can you make a quantum computer? So a quantum computer is something that we very much would like to do. So a quantum computer would be a device that can do operations on quantum bits. So bits, of course, are zeros and ones. Quantum bits are zeros and ones or quantum superpositions between the two. Okay, and a quantum computer is a device that does operations on quantum bits, with including the superpositions. Now it's a fact that if you could have a quantum computer, then there are classes of problems that you could solve much more quickly than on a regular classical computer. So that's a strong motivation for making a quantum computer. The problem is it's very hard. Okay, and the fundamental difficulty is that if you measure a state, you destroy superpositions. Okay, and so as a practical matter, then the question is, how do you keep a quantum computer from accidentally measuring itself? Okay, so this is the decoherence problem, which is the fundamental problem that makes making a quantum computer hard. And so what I'd like to describe to you is one possible solution to this problem, which is to split the indivisible, to split the qubit, doing exactly the same kind of thing that I told you about before. So, a qubit is a two-level system. I can say, you can think of it as a spin. It can be up or down. But it's something that is localized in a particular place. Okay. And so that means that if you look, you only have to look in one place in order to measure it, and then you killed any superposition. So what if you could split a qubit and split it into two spatially separated places? Okay. Then maybe you'd have some hope of protecting the quantum information. If you can only do local measurements, and if your accidental measurements are only local measurements where you look at one place at a time, then this could protect the quantum information from local sources of decoherence. And so what I'd like to show you is that in principle, it is possible to split a qubit by using a topological electronic phase called the topological superconductor. And so, again, I'm almost out of time, so I'm not gonna give you a course on superconductivity. But let me just say that the way we understand superconductors, one can understand them with exactly the same language that we understand insulators or other electronic materials. So in the mean field theory of a superconductor, the BCS mean field theory, one can describe a superconductor in terms of a single particle quantum mechanics problem that has a band structure, okay? But the price that you pay for that is you sort of have to make two copies of your Hamiltonian, okay? And in doing so, the conduction band and the valence band have an exact symmetry that relates them. So the Bogolubov-de Gennes theory of a superconductor has a band structure, but now it has an intrinsic particle hole symmetry, unlike the polyacetylene that I talked about before. Okay, so that means every state at positive energy has a partner at negative energy. And moreover, those states at positive and negative energy, they're actually really redundant descriptions of the same thing. Okay, so now you have something new though. So you can ask, well, if you have this, could you have a topological band structure for a superconductor? And in particular, could you have a zero mode where now this zero mode really would be topologically protected because you have this, again, you have a single state here, and you can't move it away from zero because its partner would have to appear out of nowhere. Okay, and so this is what happens at the end of a one-dimensional topological superconductor. Okay, so you're able to have this impossible thing, which is what we call a Majorana zero mode. Okay, now of course there has to be another one somewhere else. You can't have this by itself. Okay, but the other one can be spatially separated. And so the remarkable thing is that this basically splits a qubit. And so this is an insight that we have to have Alexei Kitaev to thank for this flash of genius for understanding this, which is that these two Majorana modes at the end of a one-dimensional superconductor, they define a single two-level system. And you can sort of think that the Majorana modes are sort of like the real and imaginary parts of a Dirac fermion operator. And the Dirac fermion operator has two states. It defines a state that's either occupied by a fermion or not occupied by a fermion. And that's a two-level system. And what a topological superconductor does is it's able to separate these spatially. Okay, and so in principle, this is possible. Now, the question is, can we make this come to life? This is a story which I don't have time to go through, but there are many ideas for how to do this, and there's been some progress experimentally. Though the progress that we've had, there's also controversy, and it's a very exciting and very active area. There's much to do. There are many venues where this kind of physics can arise. And again, I'll say this is a very active area. And I think I was going to close with some further directions, but I think in light of the time, and I realize I've gone over, I think what I'm going to do is I'm going to just go straight to the conclusion and say that the bottom line here is that symmetry and topology are this very powerful framework for understanding electronic phases of matter that have these remarkable protected low energy states, topological insulators, topological superconductors, topological semimetals, which I didn't get much time to talk about. The remarkable thing about this field is that it is a field that has a remarkable interplay between sort of conceptual theoretical physics, computational theoretical physics, and experimental physics. And there's this remarkable interplay between the two. There are many experimental challenges and many theoretical challenges. And this is what keeps us busy, and it's what's going to keep us busy for some time to come. And for the young people in the audience, I think there are many problems here to think about. So it's been a pleasure. Thank you again for the invitation to come speak to you, and I'm happy to stick around for a while to answer questions. So thank you very much.
Thank you very much for this very comprehensive and exciting talk. That was a pleasure to listen to this talk. So now we can pass to questions. Please ask questions. Questions, please. Can we unshare, Charles, to see
sure.
maybe who
Certainly.
Who raised hand or so on? Questions, please. Samet, please come. Can Artun'un sesini açar mısınız Samet? İnanç Hoca'nın sesini açar mısınız Samet? Çağatay, Erbilcan'ın sesini açar mısın?
Hocam açık şu anda. Açarsa açın.
Thank you very much, dear Charles. I wonder about the quantized electrical conductance or quantized thermal conductance. In that cases, the normal diffusion is valid or anomalous diffusion valid? I mean, the transport particles.
Well, I would say it's not diffusion. It's really ballistic transport. So the thing about the, normally in a metal, electrons, are moving, they're bouncing around, they're doing a random walk and they can diffuse. And that's the way normal transport happens. But in these edge states, the only direction that the electron can move in is forward. And so the electron's not diffusing. It's going. It's going in a straight line. And it's that fact that underlies the fact that the conductance is so precisely quantized. Okay, because you can sort of think that, if you add an electron at one end, then with 100% certainty it's going to come out the other end, because the only way it can go is forward. And so it's really ballistic transport. And so I wouldn't say that it's with there's no diffusion.
I see. I had thought,
and it's sort of the same thing is true for the heat as well. Now, of course, I'm only talking about the heat that's flowing in the electronic system. Of course, there are also phonons and other degrees of freedom, and so including those makes things a little bit more complicated. But if you think in terms of the heat that is flowing in the electronic system, then that's ballistic as well.
I was confused with disorder and with disorder.
Well, no, you see, the thing is that it can still be disordered. Okay, that's the remarkable thing about the quantized Hall effect, is that even when it's disordered, the transport in the edge states is perfect. Okay, so if you have disorder, you can imagine you have some random potential. The electrons are they're still just the only place they can go is to go forward. Maybe they go around the impurity, but they still go forward. There's no option for scattering back, okay, because there are no states to scatter into.
Why did you emphasize commensurate periodic potentials?
Well, just because it's easier to understand the energy gap that opens up when you have a commensurate periodic potential. Okay, so if you have disorder, then what will happen in a one-dimensional conductor is you'll get Anderson localization. Okay, and so the states will become localized. And that's sort of the same as what happens when you add a periodic potential. Then it becomes localized there as well. You open up an energy gap, and the electrons are just sort of rattling back and forth. They're not going anywhere. So it's easier to write down a simple model of that localization by adding a periodic potential. Okay, but the Anderson localization is for when you have disorder, is doing kind of the same thing.
İnanç Hocam, please come.
Hi. I think I have apologize because I have really bad internet. My fiber cable got some sort of accident happened. I think
well,
now
I can hear you clearly.
Okay, great, wonderful, Charlie. Good to see you. Very nice talk. So I was wondering about this, the latest from Microsoft. So because of course you're also in a place where my friend Sergey is. So I have the feeling you would have some unique insights into recent. So may I ask your opinion on the recent developments?
Other than the fact that there's controversy, I'm a little bit agnostic on that. I guess my feeling is that the experiments are probably okay. There's there are two issues. There's there's the physics that you're trying to get at with the experiment, and then there's the process of declaring victory. Yeah. And the latter is fraught with peril, right? Yeah. Because how do you know you're right, and are you certain? Okay, and I don't think we have that certainty. Yeah. But in a way, I feel like it should work, right? But it really is a challenge for experimental physics to be able to, we don't have the the simple, clean experiment that everybody agrees is right. So we don't have that. But my feeling is that this is going to be something that doesn't, there isn't going to be a moment in time where all of a sudden everybody says, yes, this is it. It's more going to be over time, we're going to get more and more confident, in these results. So I don't think there's going to be an aha moment where everybody's happy.
Yeah, exactly. I mean, I guess there's now a new, but Microsoft Labs claims that now they see the, I don't know, I don't think they claim, of course, Majorana's, but at least they say they now signatures of the topological state. But I haven't, since they're not publishing anymore, I haven't seen, or I cannot really comment. But I guess you
yeah, I wouldn't actually. I can't really say that I'm not privy to any other. I don't have any inside information on that.
Okay. All right, thanks. Thank you. Very nice talk.
Thank you very much.
Chaz, we have another question sure. In chat. Can you read this, or shall I?
Let me see if I can open the chat. Hold on. Let me just see. How do I do this? Okay. So the question is: can we connect topological conductors to form new conductors, like connected sum operation in topology? Interesting question. So first off, I'm not quite sure I know what connected sum operation is, but one thing I'll say is that when we're talking about topological conductors, the topology is occurring in momentum space, not in real space. So it's not that we have a conductor whose shape is in the shape of a donut, and then we could join two donuts together to make a two-hole donut. Okay, so it's not that. The donut is in momentum space. Okay, and so if I allow myself to join things in momentum space, then maybe one could sort of do that. Yeah, one could imagine things like that. I'm not sure that. Yeah, I mean, in a way, maybe one could say that when one undergoes a transition between two different topological insulating states, one can view that as maybe bringing together two things and joining and getting something new. So you get some sort of transition that can occur. But I think the main thing I think is that the topology that I've been talking about is happening in momentum space.
More question, please.
Okay, so the question is the Heisenberg algebra deformed in such disordered systems? My guess is the answer to that is no, but I'm not 100% sure. I'd have to make sure I understand what Heisenberg algebra is. If the Heisenberg algebra is the commutator of X and P, I think that probably stays the same.
More question, please. So, Charles, it seems to me that there are no more questions.
Okay, well, so again, thank you very much.
Thank you very much. Thank you for coming and joining us. It was a great pleasure for us, and we hope that to see you in person in the nearest
Absolutely.
future. In the nearest
Okay.
future.
Thank you so much. Okay, take care. Have a good night.
Yeah. Bye.